Okay, so I am recording this review session as well with the iPad, because I know that there are some people who couldn't make it, so that is kind of happening. I think the only people who actually are like in the views, like Hunter's head is like right in the center, so. Oh, you're good, whatever. No, you're not blocking the view, you're just visible. Okay, anyways, so if you want to watch this again, right? I'll post it on Classroom and you can see it on it'll be on a YouTube channel or whatever, so you can watch it all over, all 2 hours in all of its glory. Did I tell you about the time? Well, actually, some of you might even have been here. I had a class recorded last year to observe afterwards, and I had to like watch myself teach and then make observations about it and report on that or talk about that. It was horrible. I don't know how you guys are in terms of like watching yourself, but like that process of watching yourself, we are so bad at reflecting on ourselves, hey? Like, yeah, perceiving oneself is not easy. Okay. So, Electrochem. Otherwise known as Redox. What is Electrochem all about? Yes. Do you see the electro in Electrochem?
No.
That stands for electrons. Do you see the chem in Electrochem? That stands for chemistry. So this is essentially chemistry of electrons moving around. What I actually really like about Chem 30, and sadly it took me a while to realize this, is the fact that redox is electrons moving. And then when you look at acid-base chemistry, what's moving there? No. No. Close. Protons. Protons are moving. So the similarities actually between redox and acid-base chemistry has to do with the fact that redox is electrons, right? And then acid-base is protons. That's why they're so closely related between like OA and RA and then strong acid, strong base. It's interesting. Anyways, this diagram, critical for your understanding of electrochem or redox. You need to know what oxidation is and what reduction is. Your basic facts of oxidation is losing electrons, right? And reduction is gaining electrons. Really important. How do you remember that? Leo the lion says GERD. Or, if you want a more Alberta themed answer, oil rig. Oxidation is losing, right? Reduction is gaining. So, oil rig is another option. Yeah, oil. Oil. Okay, anyways. So that is another option. Now, actually, I think, and I did this a lot in class, the idea of reduction makes things more negative, right? So negative, becoming more negative is reduction, and that's why we go like ner, and then more positive is oxidation, so poo. That actually ends up being a better like functional way of thinking about it. So if it's getting more negative, it's going through reduction. If it's getting more positive, it's going through oxidation. The main confusion about redox is the fact that you think about negatives from math as the absence of something. In chemistry, it's the opposite. When you have negative in terms of charge, that actually means you gained electrons, because electrons are the only things that can move. So negative actually has to do with, when it's getting more negative, the gain of electrons, right, the GERD. Okay, and then my agents are the opposite of the process. So I think about reduction and oxidation as like our verbs. And then the agents, oxidizing agent, reducing agent, is like your noun. It's what it's happening to. So the oxidizing agent gets reduced. and this is where I feel like I'm just saying a bunch of words, and like, it's hard to sort it out. So let's do this slowly. The oxidizing agent is the agent for the oxidation of the other thing. It's what causes the oxidation to occur. Okay, it's the agent for oxidation. And it is the agent because it itself gets reduced. So by gaining electrons, it allows something else to lose electrons. If I want to give away my marker, it's hard for me to come up with that word. If I want to give away my marker, what has to happen? Hunter wants to give away his donut. What has to happen? Somebody has to be willing to take it. So we have to have that relationship if there's a giver and a taker. So here, the oxidizing agent gets reduced, the reducing agent gets oxidized. Those basic facts are really important. And that's what this slide is about, is that oxidation is the loss of electrons, it becomes more positive, and this happens to the reducing agents. Okay, so again, process is oxidation. That happens to the thing of the reducing agents. When I'm talking about the reducing agent, that is a reactant that I'm talking about, not a product, but a reactant. So reducing agent gets oxidized. Oxidizing agent gets reduced. There will be questions on the diploma that will actually just be about this definition. It'll like show you something like sodium becomes sodium ion in 1 electron. And we'll say, what's happening in this? And it will be, options of oxidation because it's gaining electrons, oxidation because it's losing electrons, reduction because it's gaining electrons, reduction because it's losing electrons. So you just have to realize, hey, it's becoming more positive, so therefore it's getting food, right? Oxidation, positive oxidation, which makes it then the reducing agent. The questions are that simple, many of them. It's just you really knowing your definitions. So yesterday we spent quite a bit of time on endothermic versus exothermic, right? It's like, know your facts. These facts, knowing this, comes up on many questions on the diploma. And they're pretty easy questions. You just have to really know oxidation versus reduction. Oh, the ink is still there. Don't look away. Are you looking? Yeah, no, good. Now you can look. Okay, let's actually take a look at this particular reaction. Now actually, before we get into that, we should talk about the idea of a full versus a half reaction, or a net, is a better word, versus a half reaction. What's a half reaction? Whoa, half of a reaction. What will you see in a half reaction you don't see in a net? Wrong. It's a good try though. The other half is missing. You're not wrong. You'll see electrons in a half reaction. You will not see electrons in a net. Okay, so on this, I would like you to label the OA and the RA, and also show the oxidation and the reduction occurring. And if we want to get extra fancy, you could even make 2 half reactions out of this. So break it down. I'll give you a minute to try, see where you're at. So how I would start this out, because you've gone through the full unit now, so you actually know how to do oxidation numbers. You didn't maybe when you did this the first time in the chapter, right? But now you know about oxidation numbers. So what I would do is I would start out by actually doing oxidation numbers on the top to be able to identify what I have here for charges or oxidation numbers. I shouldn't say those are the same. They're different, but they're often the same. So for chlorine, what's the oxidation number? 0. For every element by itself, right, it'll be 0. Sodium also 0. Here I have positive 1 for sodium and negative 1 for chlorine. So, chlorine went from 0 to negative 1. What kind of process did it go through? Reduction, because it got more negative. Reduction. What about sodium? Oxidation, got more positive, right? So poo, oxidation. In my mind, that's easier to think about it of, is it becoming more negative or more positive? Up to you what you think. So now that I've labeled the reduction and the oxidation, I can now figure out the agents, right? And the agents are just opposite of the process that's occurring to it. So the thing that gets reduced, that goes through reduction, is the OA. The thing that goes through the oxidation is the RA. Okay? So now how'd the half reactions go? Really good. So let's do chlorine first. I have Cl2 gas. I think the best way to go about this is then to draw the arrow and draw what it's making, which is 2Cl minus aqueous, right? I'm getting 2 chloride ions from that chlorine. Now I need to make sure the charge works out. I know that it's reduction, because I already labeled it as reduction. So that means that I'm going to have electrons as a reactant. Do you notice how they both start with Re? Reduction, electrons are a reactant. So I'm going to have electrons on this side. How many electrons do I need to make this work? I'm going to say this over and over and over again in this chapter, but there is a way to cheat on multiple choice for Redox. And that is, you check every single option on the multiple choice on the diploma, and you see if the charge is even between reactants and products. There will be options where charge does not balance between reactants and products. It doesn't work out, it's not equal. If that's the case, it's not a valid reaction. And I'm talking about half, net, it doesn't matter, okay? Charge always has to balance on both sides, it has to. Otherwise, mass is not conserved. Okay, so I get 2 chlorides out of that. And then I've got sodium turning into sodium ion. And I need an electron on the right to make this balance out, right here, and I'm done. What's interesting is that my coefficient 2 isn't needed here. I always want the lowest numbers possible, right? So I don't automatically take that 2 and put it here, take that 2 and put it here. I start the half reaction and I work it out. So here I just need 1, 1, and 1. Okay, so that is my reduction and my oxidation. Any questions on that? Lisa? Good. I really should have erased all this first. So I'd be embarrassed. Look away! Okay, much less explanation for this one, but I want you to try this out and try to get the half reactions done. See how it goes. And while you're doing that, I'm going to freeze the screen and erase all the slides. 0 for calcium, becomes positive 2. When I look at other stuff, hydrogen is positive 1, goes to 0. So I've already actually found both. We can do oxidation numbers for everything here and work it out. So based on the fact that oxygen is normally negative 2, right? I got negative 6, positive 1. This has to be positive 5. So we're skipping ahead a bit here to oxidation numbers, but that's fine. This will end up being the same. Knowing that nitrate needs to come out to negative 1 overall for a charge, I have negative 2 times 3 is negative 6 plus 5 gets me negative 1. Okay, so calcium is going from 0 to positive 2. So it's becoming more positive, meaning that it is going through oxidation, right? Ooh. So that's your Ra. And then hydrogen ion is actually going from positive 1 to 0. So that's getting more negative. That's your reduction, which makes it your OA. So what I've got here is Ca solid. Reacts to form Ca with the 2 positive charge, right, calcium ion, and 2 electrons. So I need the 2 electrons to balance the charge on both sides, and that's why it's oxidation, is because the electrons are a product. So just that fact of like, in oxidation, electrons will be a product, really important. Then I have hydrogen ion here. So H positive aqueous, making H2 gas. So just getting it straight from here, H positive, H2 gas. And the reason why I can split this up, by the way, HNO3, I'm kind of skipping a little bit there. But the reason why I can split that up is the fact that it's a strong acid, right? So I can split it up into H positive and nitrate. So in order to make this work, I need to make sure I have 2 hydrogens going in to match the 2 I have coming out. And then I have 2 electrons as a reactant in order to make that work for charge on the left and the right. Okay, that's it. So this is my oxidation, and this is my reduction. Good for that? It's going okay? So we're actually going to get into half reactions that are a little bit more complex. Right here, it's kind of spelled out for you that in reduction, electrons are reactants. Well, in oxidation, electrons are a product. So again, just important to realize that. Relate that as well to the idea of endothermic and exothermic. In endothermic, where it's gaining energy, right? Energy is going in, energy is a reactant. In reduction, where I'm gaining electrons, electrons are reactants. In oxidation, where I'm losing electrons, it's a product. Just like in exothermic, when I'm losing energy from the chemical, energy is leaving, it's a product as well. So we have these kind of overlapping ideas or things. And then always reduce the coefficients to get the lowest whole numbers possible. So here's another one. I feel like we actually just kind of did this with the last one. So I think we're actually going to maybe skip this slide because it's super similar as well, and just go to the building of complex ones. So complex half reactions, and actually just full net reactions, a lot of the same things apply. When I build a half reaction, you may have to actually add water and H positive before you add electrons to make it work. Okay, so often when it says something like an acidic medium, or you have no source of oxygens or whatever, you have oxygen on one side, you have to make it work by adding water or hydrogen ions. So, yeah, add water for any unbalanced oxygen that you have. After you've done that, you're going to add H positive for any unbalanced hydrogen if it's in an acidic medium. And then after that, you're going to balance the charge using electrons as a term in either the reactants or the products. And that's what determines for you if this is oxidation or reduction. I'm talking too much. Why don't you try out this one right here? I know that I haven't gone through the process besides the steps, but try this out. See how you do. See if you struggle. So chlorine is converted to perchlorate ions in an acidic solution. Write the half reaction equation, and then is this oxidation or reduction? So backing up just a second here, based on the fact that it's a half reaction, what do you know you're going to have? Electrons. So you'll have electrons as a term in your half reaction. Let's try it out. Water, H positive, hydrogen ions, then electrons. And I'll be right back. Yeah, for sure. So this is your starting point. Cl2 gas produces the perchlorate, ClO4 minus. Are my chlorines balanced right now? No. How do I balance my chlorines? Let's put a 2 right here. I got a new problem. It's a new problem. 8 oxygens, I can't have 8 O's here and no O's over here. I don't have a source for O. So what do I use as a source for O? A little bit of water. So let's use 8 H2Os. Okay, now I got 8 waters to balance out the 8 O's from the right, but now I've got 16 hydrogens just floating on the left with nothing to balance it out on the right. So I'm going to add to the right 16 H positive aqueous. And then I take a look at my charges. On the left, I have a charge of 0, because 0 and 0 is 0. And on the right, I have 2 negative, right? 2 times 1 negative, and 16 positive. So I have 14 positive on the right. So how do I get rid of 14 positive to make it equal to 0? Throw some electrons on it. Add 14 electrons to the right to make that work. So at this point I should double check, right? And go through and make sure that everything balances and works out, which it does. I have 0 on the left and 0 on the right in total. So I'm done. So this is a half reaction because of the fact that I have electrons as a term in the actual equation. At this point, is it oxidation or reduction? It's oxidation. And it's oxidation because I have electrons as a product. In other words, it's losing electrons. No. Here's why. -2 for oxygen, right? So that's -8. So this is +7 for an oxidation number for chlorine. This was 0. So it's getting more positive. So it's. Sir, I'm foggy today. Did you say oxidation or reduction? Did you say it's getting more negative or positive? Negative. It's getting more positive. It's all good. It's all good. That's why you're here, right? We're all just safe place of learning. Relearn, yeah. Please, like, if something's confusing, let's talk about it. Let's talk about it. No? All right. Yeah. Okay. Cool. Let's move on. Do you want to try this one? Yeah. Give it a go. Okay. So, give you a little bit of time. Try it out. I mean, here's the beauty of all this, right? Let's say that you're realizing right now, I do not remember Redux. It's okay, you got time. It's Friday. You've got 3 beautiful days of studying left over. So make a note of what you're having a hard time with and then come back to it. Hello, Ben Moon here. Hey. Sure, yeah, I just got a Chem 30 review session going, but I can, if that is fine, then yeah, for sure. Yeah, sounds great. Okay, perfect, thank you. Did we get this starting right? These two things?
Yes.
Did we get that?
Yes, sir.
Good. So, with this, I look at manganese and I have 1 on the left, 1 on the right. So manganese is looking good. So now I look at oxygen, right? I have 2 on the left, 0 on the right. So I need a source for oxygen. That's going to be water. So I'll put 2 H2Os on the right in order to equal out the 2 right here. Now that I've got that, I have a new problem with hydrogens, that I have 4 hydrogens on this side and 0 on this side. Based on the fact that it's in an acidic environment, I can add hydrogen ions. That will go on the left. So I have 4 H positive on the left-hand side to balance out the 4 hydrogens over there. And now I take a look at charge on both sides, and I have positive 4 on the left, and I have positive 2 on the right. Yeah, positive 4, positive 2. I'm always adding electrons to the more positive side, right? So electrons are negative. The whole idea here is I'm trying to make both sides equal. So electrons will add to the more positive side, which is the left in this case. By adding 2 electrons, I'll sneak them up right here. By adding 2 electrons to this, I now make this a positive 2 overall charge on the left to equal the positive 2 on the right. Hooray! I'm done. Oxidation or reduction? Reduction. Electrons are a reactant. So, yeah, reduction. How did that go? Good? Better? Okay. All right, spontaneity. We know a reaction will happen, a redox reaction, if the OA is above the RA. In other words, it's downhill going from left to right. That means that the reducing agent is able to pull the electrons away from the oxidizing agents. So for example, if I take chlorine and I react chlorine with water, sure, this is a downhill. Okay, my OA is above my RA, so it's going to be happening. Okay. So what you'll do in a lot of questions is you'll just list all the stuff you have, all the major entities that are present, and then you'll identify where your OA is and your RA is. You start at the top left, keep on going down until you find something you have, that's your OA. And you go from your bottom right, work your way up until you find something you have, and that's your RA. And then if it's downhill, it's spontaneous. If it's uphill, it's non-spontaneous, which means it doesn't happen. We can use this fact in order to actually build redox tables. So when I take a look at a reaction like this where it says no reaction, I know that the OA is actually below the RA. So this is uphill. I like to imagine a little sled here. Right? There's the sled. Is the person on the sled having a good time? No. It's not spontaneous. What about this sled? Whee! We're having a great time. Okay, so this is downhill, right? This is uphill. It's not happening. The problem is then students draw the sled here and they get confused. It's always left to right. Left to right.
Where would you like them?
There's actually fine.
I have to take the car back with me.
Oh,
so,
I see, I see.
Yeah.
Can you please try this out and see if you can build a quick redox table? If you are lost, start by just identifying the OA and the RA.
And this is yours, because the textbooks are already signed out to you.
it's just on the spine.
And they're actually already in order. So if you upload them in order, like 120 is
So this is actually kind of in reverse. Is this your job for this afternoon?
Yes.
Nice. Okay, so indium, being a metal, would make a positive ion if it were to react. We don't see that in another reaction, which is unfortunate, but we know that indium is a metal, so it's going to make a cation. So based on that fact, that it's becoming positive if it were to react, you know that it goes through oxidation, making it the reducing agent. Now, P4, I can actually see it right here, becomes negative. Also, it's a non-metal, right? So it would become an anion. So it gets reduced, which makes it an OA. So P4 is my OA, indium is my RA. Just like over here, P4 will be my OA, and niobium-3 will be my RA. So here's the information that I get from this. Based on the fact that indium and phosphorus do not react, I know that this is an uphill reaction. So what I have then is that indium is right, always go on the left. P4 is right here, and indium will be uphill from that, right here. Okay, so this is uphill. And OA is always on the left, RA is on the right. Okay. So uphill because this is a no reaction at this point. Then if I take a look at the next one, I have P4 as my OA and niobium-3 as my RA. That is spontaneous, so my niobium-3 will be right here. In other words, it's downhill. Okay, so now completing these half reactions, I have P4 solid becoming P3 negative. And I can actually get that straight from this reaction right here. I'm not guessing, I can see, or you could get it from your periodic table. But I get P3 negative. I need 4 of these to make that work, right? 4 phosphorus, which actually means I'm adding 12 electrons to get the charge to balance. So that's my half reaction there. Niobium-3 from niobium-5, so I have Nd5 positive aqueous. I need 2 electrons to make that happen, to make niobium-3. And then indium, I actually don't remember, I think it's 3 positive. positive? Yep. Okay. So how would the diploma question look for this? It would ask you something like, what is the strongest OA? And you would not be able to know that until you actually end up building the table, right? To be able to tell where your strongest OA is. And maybe, I'm assuming here, what is your strongest OA? Indium-3 positive, right? It's right here. This is on your redox table from the data you have. This is your strongest OA that you have at present. What if the question instead said, what's your strongest RA? Right, niobium-3 positive right here. If I go from niobium-3 to niobium-5, what process is taking place? Niobium-3 to niobium-5. Oxidation, how do you know? It's getting more positive. It's losing electrons. Okay, so another question you could have is actually rank the OAs from weakest to strongest or something, right? And it could be a numeric response where they actually have given all these different chemicals numbers. You'd have to say, well, it's this, then this, then this for OAs. For RAs, it would be this, then this, then this. For weakest to strongest. Any questions on redox tables? Are we feeling okay about that? The big thing here, right, is realizing that when it's spontaneous, OA is above the RA. That's the whole kind of backbone of this. Way less explanation. I'm going to give you a head start on this. You try it out, and I'll do it on the board in a minute here, okay? So I'll just give you a head start, and I'll do it. You can see the answer. I'm not going to spend much time explaining it. First step is finding your OAs, your RAs. answer. Good. Lines I got from this, like how this was determined. CO2 positive to indium. I should use a color. Spontaneous, so downhill, right? CO2 positive, CO, so downhill. And then CO2 positive PD, non-spontaneous, that's uphill. And then from there, I just build the rest of my half reactions. What's your double checking process? What should you do? Well, a few things. I guess number one, check your charges, right? Make sure it equals on both sides. So 0, 0, 0, 0. Then the other thing you can do is kind of go back to the reactions and just make sure it works going the other way, right? So cobalt 2, indium, check, make sure it's spontaneous like it is here. All right, awesome. Predicting redox reactions. This is the type of question where it tells you essentially what's happening with chemicals. So say this and this is mixed, and you have to figure out what the reaction is and if that reaction is spontaneous or not. So what you do here is you list your major entities, all the stuff you actually have in solution hanging out. Then you find your SOA by going from the top left, working your way down. So you find something, you find your SRA from the bottom right, going up. And then you figure out if it's spontaneous from there once you make your net reactions. So we'll go through an example, but I'm assuming that you're somewhat familiar or remember this. What major entity will you always have? Water. So, don't forget that because water is often involved in these redox reactions. We use it a lot. So, a chemistry teacher bubbles some chlorine gas through a magnesium iodide solution. So what I would do right now is I would list all the major entities that I know that I have based on the question. So, bubble some chlorine gas. I know then that I have Cl2 gas. Through a magnesium iodide solution. Magnesium iodide, is it soluble or insoluble? Is it solid or aqueous? I actually don't know, I forget. I feel like it's soluble. It's a solid. Oh my goodness.
It's solid. It's soluble.
Yeah. Also, it does say solution, so we can kind of assume it's aqueous from that. So if an ionic compound does dissolve, what does it do? Associates. It goes to ion. So I have magnesium ion, Mg2 positive aqueous. And I have iodide ion, I minus aqueous. What am I missing right now? Water, H2O. This is a side note. If this said acidified or acidic, what else would I write here? H positive. H positive. Okay. So I got chlorine, I got magnesium ion, I have iodide ion, I have water. So now I would look at my table here. And I would start at the very top left and I'd work my way down till I find something. And oh, there it is, there's chlorine. I found Cl2, that's my SOA. So that's the strongest oxidizing agent that I have present. So I right away would kind of label that. Now, on your diploma, you're circling that sucker on your data booklet, right? It's a one-time use data booklet. It's done after you use it. So you like go nuts kind of circling and doing things on that data booklet to make sure you keep track of what you have. And then I go from the bottom right and I go up and oh, there's magnesium solid. Is that the same as what I have? No. A magnesium ion. So I keep on going up, I keep on going up, I keep on going up. Oh, there it is, 2I minus. This is my SRA. So important to realize I didn't have the 2 in front of this. That's okay, I don't care about the coefficients. But the rest has to be identical. So now I can actually build my redox reaction. What I have for reduction is I have Cl2 gas plus 2 electrons makes 2Cl minus aqueous And then I have 2I minus aqueous makes I2 solid plus 2 electrons. Is this spontaneous? Yeah. My chlorine as an OA is above my iodide as an RA. This is a downhill reaction. So for my net, I now just combine the two. I'm really lucky with this reaction because the electrons are equal in both. So I have 2 in the reduction, 2 in the oxidation. So I don't have to do any multiplying. It's already ready to cancel out on both sides. I can just combine. So I end up with Cl2 gas plus 2 iodide, 2I minus aqueous, makes 2Cl minus aqueous and I2 solid. And that is again spontaneous. Okay. So I think there's another one here, right? Maybe. Be good?
Yeah.
So why don't you try this one out? This is actually kind of a neat one. So try this out and see how it goes. Artist?
Just about the question.
Yeah, sure.
The copper can be aqueous, like copper.
No, it's solid copper. So, nitric acid is a strong acid. So I have then H positive aqueous and NO3 minus aqueous. So I'm ionizing it into those two ions. If this was a weak acid, it would stay intact, okay, but be aqueous. So it would dissolve, but it doesn't ionize. I have a copper penny, so I have Cu solid. And then finally, of course, I have water, always water. So, starting at the top left and working my way down, I actually have a nitric acid reaction that's kind of like, I don't know, quarter of the way down? Yeah. So 2NO3 minus plus 4H positive. So I actually have like this nitric acid reduction half reaction. So this is my SOA right here. H positive and nitrate together. And then working my way up, I end up with copper right here. So that's just over halfway. So that is my SRA. And right away, I actually note that this is spontaneous. So I have a spontaneous reaction here. So I would end up with 2NO3 minus aqueous plus 4H positive aqueous plus 2 electrons makes N2O4 gas and 2H2O liquid. Okay, and then for the SRA, my oxidation, I have Cu solid, reacts to make Cu2 positive and 2 electrons. I really wish for this one, the electrons didn't work out. I really probably should change this for next year so we have one where the electrons aren't the same. If, and I'm not going to change the number here, but let's just pretend like the electrons for this was 1. It was Cu solid to Cu1 positive aqueous, 1 electron. What would I have to do? Multiply this by 2, yeah. Before I combine to make a net, I have to have electrons equal and reactants and products in the half reactions. But anyways, it's not this problem. Here I've got 2 and 2, so I can just go ahead and combine. So I get 2NO3 minus aqueous plus 4H positive aqueous plus copper makes Cu2 positive aqueous plus N2O4 gas, I'm out of room, and 2 waters. This is a fun reaction to see actually, because N2O4 is like this brown poisonous gas that gets made. So it actually makes like this brown, like bubbles like crazy, you get this brown gas coming off of it. And then the copper 2 ions are like a blue color, right? You actually get some copper 1 ions as well. So you get this blue-green solution with just like brown gas coming off of it like crazy.
So it looked like.
But you don't breathe it in.
But don't breathe it in.
Yeah. Sorry? I mean, we could.
Copper tea is my favorite.
We always could. Everything in life is not. Do you feel like that would be beneficial for you? Okay, yeah, let's do it. So, ionic, we'll kind of split this into a few different like types of classes of things. I have ionic, I've got acids, I've got elements, and I went in weird order here. I also have molecular. Okay, so for ionic, I got 2 options. I either have solid, so insoluble, or soluble. How do you know which one it falls into? Solubility table. If it's soluble, it dissociates, and hopefully that makes sense of, you know what that means? Into 2 ions. So 2 aqueous ions. If it's insoluble, it stays intact.
It's just aqueous, right?
Actually, as a solid, it just doesn't dissolve. It's just kind of hanging out as chunks. Acids. I have two options for an acid. I have either strong or weak. How do you identify it's an acid? How do you know?
The H.
Yeah, it starts with an H or ends in COOH. So that's your like indicator of, hey, this is an acid. Strong ionizes to H positive, aqueous, and anion. Weak, intact, aqueous. So it's going to dissolve, but it does not ionize. It stays intact as an aqueous. Elements are the best. They're the greatest because they do nothing. Nothing at all. They stay in the original state, just hang out. And then molecular, you have a list of molecular compounds you should know dissolve. This actually doesn't matter much, thankfully, for redox. It doesn't come into play very often. I feel weird saying it, especially on a recorded video. It's the shag me thing. Remember? Shag me. So sucrose, hydrogen peroxide, ammonia, glucose, methanol, ethanol. Okay.
Oh, that's a good one.
So those are the ones that actually dissolve, that are molecular. Basically, here's the thing. If it has hydrogen in it, look it up. Okay? Hydrogen is the thing that is in common with all of those. Ammonia, NH3. So I can give you that list. Thankfully, this doesn't actually come into play very often for this stuff, right? But dissolves would be, you want formulas? Is that easiest? Or names? Formulas, so C12H22O11, right? For sucrose. Hydrogen peroxide, H2O2, that's a thing in this. Ammonia, NH3. Glucose, C6H12O6. Methanol, CH3OH. Ethanol, C2H5OH. Now you actually have the background information as well from organic to know that alcohols do dissolve because of the fact that they're polar and tiny, right? Have hydrogen bonding. All right, cool. So everything else for molecular, if it's not on that list, we just assume that it stays its original state and doesn't dissolve. Okay, oxidation numbers. Oxidation numbers are typically just really nice and simple and easy. Right? If you memorize the rules, you're in a good place. And there's typically like 2 or 3 questions that kind of involve oxidation numbers. There will probably be a numeric response. What they love to do is focus in on one element, let's say manganese or carbon or something. And then they give you a bunch of different compounds, or I shouldn't say compounds, a bunch of different things that have manganese in it. And you have to figure out what the oxidation number is for all those things. And then it would be 4 different spots on your numeric response. Before you go through the rules, can we just try one and see if you can actually do it? See where you're at? You tell me the oxidation number of oxygen in these things. H2O. O2, O2 negative, and H2O2. Let me get my copy. It's great. Yeah. Okay. H2O. What'd you find? -2. This is the normal rules for oxygen, right? Whenever it's in a compound or whatever, we start with -2 for oxygen. O2? Why? Element. That? This is actually the one that normally is the worst done. Isn't that fun? It is -2. It is -2. It's just the ion charge, right? But often that's one that people mess up on. Because they think it's more complicated. But it just has to come out to the charge, right? So it's got to be -2. No. -1. Why?
Peroxide.
Peroxide. I actually think that this is going to be on the diploma this year, H2O2. Because they brought it up in the information bulletin around peroxides. So I think they're trying to prime teachers for like, focus on this. Do you know structurally what makes a peroxide a peroxide?
Is it like all that? Is it like that?
I don't know what that means, but yes. Kind of. Yeah, it's the two rows are attached. So what I actually have is, this would be kind of the structure. It's two V shapes. And this is always twirling around, so not that that matters. But the reason why it's -1 is oxidation numbers is all about who do the electrons belong to. In OO bonds, they don't belong to either because it's even, right? Even electronegativity, they both try to hog the electrons. So therefore, those two electrons don't count for either one of them. But it gets, the hydrogen electron gets hogged, making a -1. This one's -1 as well. And then this is evenly shared. If that confused you, peroxide, -1, end of story. That's what you need to know. These are your rules. You should have this memorized for sure, okay? So all atoms and elements at 0, not complicated. Hydrogen, almost always +1, but if it's a hydride, meaning it is with a metal and it's an anion, then it's going to be -1. This doesn't come up very often, but it is a thing. So for example, lithium hydride, it's -1 for the hydrogen. Oxygen almost always in a compound is -2, except for peroxide. We just talked about that. There is -1. Again, I think it's going to be on the diploma this year. I'll be surprised if it's not. Okay, and then monoatomic. It just has the charge for its oxidation number. So, oxidation numbers also can be fractions, which is fun, right? Especially for carbon. That happens quite a bit. And fluorine is always -1 if it's in a compound. And the reason why is it is most electronegative. When in doubt, if you forget the rules or whatever, the most electronegative thing is going to get its charge. So fluorine being the most electronegative element, it will get its charge of -1 as its oxidation number. Gets its way. Fluorine's crazy. That's why oxygen is almost always -2. Right? It's very electronegative. So it gets its charge. Okay. So here are 6 glorious examples. Why don't you quickly try them out, label the oxidation numbers for all of the different atoms. Take it up in a second. The way that I like to do this, and I'll show you one example, is I like to put the oxidation numbers on the top, and then I like to multiply and do my totals on the bottom. I think it's a good method. So if I was showing you, let's say number 3, I know that oxygen is -2, because it is, and hydrogen is +1. So I would label those two first. Then I would multiply and do my totals down below. So +1 times 2, I have +2 from hydrogens, and I have -2 times 4 is -8. These are my oxidation numbers on the top. Down below is just work. Doesn't mean anything. Okay, it's just work. I need this whole thing to come out to -1. So that means that the phosphorus is going to have to be positive 5 in order to get out to negative 1. So positive 2, positive 5 is 7, minus 8 is negative 1. So phosphorus, because I only have one of them, will be positive 5 to make that work. So on the top, these are my oxidation numbers, positive 1, positive 5, negative 2. All right, why don't you try out the other 5? Just generally being in this room for a significant amount of time, do you find the fish tank calming or a distraction? It's nice here in the water. Well, it's funny because it turned off during the science 10 exam, and it was too quiet, and you could hear everything that was happening, right? Having some white noise is actually kind of nice, I think. Yeah.
I kind of like the water. You're like, yeah, you're like, oh, let's watch TV while we study.
Yeah, just the water. It's just the water.
Okay, when I was bringing in that diploma, at one point I looked up and I just saw every single fish pointed at me, were like just staring. I was like,
Was watching you?
I'm like, I think it was just like.
Do they have disappointing looks on their faces?
It looked like.
Zach stats, yeah.
Then they start like throwing pebbles at it.
What if they start getting like really intelligent so they know what's chemistry?
That's what I thought. Is like, what if they're just quickly really super.
We set them down wherever.
Well, how many teaching them every day, so.
What if that was the first person to really sentient fish?
Science.
So I was
Right
yesterday.
now.
Put in his car.
Oh, yeah, you said it. It's certain soda.
Yeah, but like, like you could like put like a plastic bag.
Nice to this. Zach's the type of guy to try poetry.
What's her? No, I come in.
Really?
Every 3 or 4 days.
Are they hyped when they see you? Like, oh, my boy, they slap down.
You might like one day just start jumping into it.
Yeah.
I don't know, do you feel like one day you might.
These are minutes on some little
Let's do that.
I don't know, do you think one day you might really have large
They want it to make, I think, as comfortable as possible in the phosphorus here. They use it for movies.
I don't have a lot of drummers though. I don't.
That's my theory. Okay, so I hope this is what you did as well. Does that match what you have?
See.
So CO2, positive 4, negative 2, NO3, positive 5, negative 2. Comes out to negative 1, right? In totals, positive 5, negative 6. Here I have positive 6, negative 1, so I get 0. Here it's coming out to 0, because I have negative 8, positive 2, positive 6. And then here, this one's interesting. Fluorine gets its way, it's negative 1, which means oxygen has to be positive 2 in order for that to work. Okay, so typical kind of weird diploma question of giving you one element you're focusing on in 4 different things and saying, okay, find the oxidation number for whatever in these 4 different compounds or chemical species. So here, if I'm doing carbon, I would need to come up with all 4 different oxidation numbers for carbon. So why don't you quickly try that out, and then I guess we got to start speeding up a bit. But this chapter 13 takes a lot more of the battery stuff.
And so, when I look at CH3OH, do I want to count the OH as
everything of the same element you want to treat as one thing.
So this would be like, I have 4 H's in here.
Exactly. Yeah, so don't worry about it being written in 2 separate places, just all hydrogens are treated equally.
Okay, and then is it okay if I have 0 on my carbon?
Totally okay. Yeah. Got a cup? Ready for this? Just a school topic, nice to talk. Way back from the day. It's cool.
Does the hydroxide
For which one, sorry?
B, so you count the hydroxide as 1 or
How do you? No, count all H's as 4 H's, so you have 4 positive. And then do your O as negative 2. And then go from there.
well, wouldn't it be negative? The H's would be -1.
Okay, so in order for this to work, first one is going to be -4, right? The 4 positive ones, so -4 here. In this one, I have +4 from hydrogen, -2 from the O, so carbon has to be -2. In C, I have -8/3, which is weird, but I can have fractions, it's fine. Remember again, oxidation numbers are just a form of electron bookkeeping. It's not actually like really connected. I don't want to say that, but don't take it as there's actually, -8/3 electrons extra on every carbon. It's just a way for me to keep track of where they are. But it's not necessarily reality. And then for D, I have 0 on the carbon for an oxidation number. All right. You can use oxidation numbers to balance chemical reactions. Then sometimes you have to add hydrogen ion or water to make it work. Especially if it says acidic medium, right? You can have hydrogen ion at your disposal, and then water can be used whenever you have aqueous stuff to be a source of oxygen. But the idea behind this, and I feel like often this becomes very convoluted in the actual course, it's all about electrons lost has to equal electrons gained. So whatever is lost in the oxidation, that number of electrons has to be gained in the reduction. So I just have to make sure it's equal. And by making it equal with the coefficients and the reactants, I can balance the rest. So what do I have here? I've got 1, 2, okay, so I'll do one, you can do the other. And then thankfully we are off to the next chapter and we'll run through that in half an hour. And we should be done on time, hopefully. I feel like I'm moving slower today. Now, where did I put my blue marker? I have no idea. All right, we're writing it up here. Okay, so chlorate ions and iodine react in an acidic solution. Ooh, so acidic means I have H positive to use. That's fun. I can use H positive if I want to. To produce chloride ions and iodate ions, balance the equation for this reaction. Okay, so chlorate is ClO3 minus, right? I think. I don't know why I always get confused between chlorate and perchlorate and stuff. And iodine, what's iodine? I2, right off wrinkle, I2 solid. To produce chloride ions, so I have Cl minus aqueous and iodate, IO3 minus aqueous. Okay, now I'm going to look at my oxidation numbers for this stuff. Let's use a different color. Let's go with green. So -2 for my, that does not show up very well, does it? All the time. All the time. I don't know. You need a whole thing to check. It would take seconds. Yeah, okay, 0, and then this is -1, -2, +5. So these are my oxidation numbers. So what I have happening is I have +5 changing to Cl-. How many electrons were gained by chlorine in this reduction? 6. Really important to consider the positive to the negative. So I have a 6 electron change from this to this. The way we did this in class is we focused first on the atom. So I said 6 electrons per chlorine. And then I said, okay, well I have 1 chlorine for each chlorate. So it's 6 electrons total for the chlorate, for the full reactant. And I'm only looking at reactants right now for this. For iodine, I go from 0 to +5. So it's 5 electrons for an iodine atom. So how much is it for the full iodine as I2? 10, right? Because I have 2 I's in iodine. So I have 10 electrons for the I2. Are we good for what I've written so far?
Yeah, that's not a great choice.
Okay, so +5 to -1, 6 electrons, right? 1 chlorine, so 6. I2 is 0 to +5, so that's 5 electrons per I, and I have 2 I's, so 10. Now what I'm doing is considering the lowest common multiple between 10 and 6. So where do 10 and 6 meet up first? 30. So I'm going to have 3 of these to get to 30, and I'm going to have 5 of these. So 5, this is just determining the number I'm putting in front of my reactants. So 5 chlorates, 3 iodides. Those numbers are now set in stone. They're done. Hooray. Now I can work out the rest. So because I have 5 CLs, I need 5 of these. And I now have 3 times 2 is 6 I's, so I have 6 of those. So chlorine balanced, iodine balanced, and electrons are balanced. But now I need to worry about my O's and my H's. For O's, I have 15 on the left, and I have 18 on the right, and this is going to get so ugly. But I need to sneak in 3 waters here for reactants to get to 18 O's on both sides. So 5 times 3 is 15, plus 3 is 18, but I have 6 times 3 is 18. Okay. Now I have 6 H's on the left with no H's on the right. So I can add 6 H positive on the right-hand side to balance out those H's. And I can do that because it's in acidic solution. So I have H positive at my disposal. Now I can double check. On the left-hand side, I have 5 negative of charge, right? On the right-hand side, I have 5 negative, 6 negative, 6 positive. So those cancel out. I have 5 negative on the right. So I know it's good. It works. Why don't I have electrons written here? It's a net, it's not a half. It's a full reaction. Try one out on your own. Try out the next one. See how it goes. So this meets up at 12. I have 2 electrons per carbon, so 4 electrons per ethanol. And then I have 3 electrons per chromium atom, so 6 electrons per dichromate. So it meets up at 12, so I have a 3 in front of ethanol to get to 12, and a 2 in front of dichromate to get to 12. Now I go to the right-hand side, and that means I have 4 chromiums, because 2 times 2. And I have 6 carbons, so I need 3 of these to make that happen. So I have 2 times 3 is 6, and 3 times 2 is 6. So now that's worked out. Now I'm going to look at my O's and my H's. On the left-hand side, I have 3 O's plus another 14. So right now I'm sitting at 17 oxygen. Now on the right, I have 3 times 2 is 6 O's. So I need 11 waters on the right to make that work. Now I look at hydrogen. On the left, I have 3 times 6 is 18 hydrogen. And on the right, I have 3 times 4 is 12, plus 22, gives me 34. Big numbers here. So I need 16 H positive to make that happen. This is really easy, right, to make a mistake, but thankfully we have a way to double check our work and make sure that we're on the right track. So now what we can do is we can go 16 positive plus 4 negative. So I'm at 12 positive for a charge. So just double checking right now. And on the right-hand side, it's 4 times 3 is 12 positive. So I know I'm correct based on the fact that the charge equals on both sides. So good way to double check. So how would this look on the diploma? Yeah, what they would do is they'd ask you like, what is the coefficient on ethanol and chromium 3 and let's say water or something. Like they'd pick a few things, not the whole thing, and ask you what the coefficient is when it's balanced. They might mix it up and say something like chromium is, reduced for a multiple choice or something like that. But anyways, that'd be the format. All right, we got to move quick. Electrochemical cells, we have 2 types. We have essentially voltaic. And we have electrolytic. Very important to know the major differences between these 2 types. There's always, or I should say almost always, a question that has to do with the type of energy conversion that happens in these. So for voltaic, it's chemical to electrical. This is your normal kind of cell that's within a battery. So chemical energy is changing into electrical energy. Electricity is produced. Electrolytic is actually the opposite. In electrolytic, I have electrical energy being converted into chemical energy. So what I'm doing is I'm actually like plating something. When you recharge a battery, which is a secondary cell, right? When you're recharging a battery, you're actually making it an electrolytic cell during that time. You're storing energy back in it using electricity, and then when it's discharging, it's a voltaic again. There's a really good question on, it was on your quiz or something as well, in the diploma, asking about a car and saying, when the car is running, or starting, sorry, when the car is starting, it's a whatever type of cell. Okay, and then when the car is running and the alternator is recharging the battery, it's a blank kind of cell. And knowing that would allow you to answer it. Okay, so how do you identify which type it is? In a voltaic cell, typically you will see separate containers. Okay, so you'll actually see 2 different beakers or whatever it's in, and then you'll see some kind of porous boundary like a salt bridge, or alternatively you'll have a beaker and then a porous cup inside of that. So really it's still like 2 separate containers, right? The reason why you have to have 2 separate containers for voltaic is you have to keep your OA and your RA separated. If your OA and RA aren't separated, there's no reason for the electrons to go through the wire. They can just go directly in between. Okay, so OA and RA have to be separate. At the cathode, you have reduction. Fat red cat. Think about, again, Clifford, the cat version. Okay, fat red cat. So what's happening is that the cathode typically will grow, not always, but almost always, will grow larger, get fatter, and it's reduction occurring there, and it's the positive one. Cat's always positive in chemistry, except for electrolytic, but we'll talk about that. Anode is negative in oxidation. The inappropriate way to remember that is the anorexic ox thing. So it is shrinking, right? Because of the anode, oxidation is occurring. All right, electron flow is always from anode to cathode. It's from A to C. It's alphabetical. So electrons go from anode to cathode, and you could work your way to this by knowing that oxidation is losing and reduction is gaining. So red cat gets fat, anorexic ox gets skinny. And ion movement is really easy as well, because anions go to anode. And cations go to cathode. Okay. When I talk about electrolytic, students right away want to go to everything's different. It's not. There's only one thing that changes on this. Do you know what changes?
Positive and negative.
Positive and negative. That's it. When you see electrolytic, you panic, right? Panic. And I'm skipping ahead. Skipping ahead. Come on. Whatever. Okay. Let's just go back to the slide. Electrolytic, panic. Which stands for positive anode, sorry. Yeah. Negative is cathode. Now you're right, often electrolytic won't have a porous boundary, but it could. Doesn't. It's not necessary anymore because it's not a spontaneous reaction, but it could. Okay, so panic, positive anode, negative is cathode. That's what panic stands for. All right, cell notation. One straight line is a phase boundary, and then when you have two straight lines, it's a porous boundary, so like a salt bridge, porous cup. Salt bridge, porous cup. Anode is first. So anode, then we have a phase boundary, which means, the electrode itself is a solid, and then the electrolytic nucleus. So that's the phase boundary, is saying they're different states. That's all it is. So I have a solid, typically, then I have aqueous stuff for the electrolyte, and then that means porous boundary, so an actual separation with allowed ion movement in between, another aqueous thing, and then a solid thing for the cathode. So you should memorize that anode is first. That will always be the case on the diploma. It used to be that way, but now they recognize that anode should go first. So that's cool. So here is a Daniel's cell, the copper zinc cell. And we could label some stuff to figure out some things with this. Yeah. NO3. What at oh, good points. Don't know. Let's just cross this out and put some sulfate in there. Sulfate. Oh, no, it's not. I don't need the brackets anymore. I didn't tell you, didn't have the cell notation, how would you figure out what the anode and the cathode is? Do you have a way? You'd have to look at your major entities and rebuild it. You know it's voltaic based on the fact that you got a voltmeter there. Yeah, voltmeter pretty unexciting if it's electrolytic, it's just zero. So you got a voltmeter. And also two separate containers, so you know it's voltaic. So now what you do is you look and you figure out your major entities. You've got zinc, right? Is that in solid? You got that into positive aqueous. You've got Cu solid, of course. Cu2 positive aqueous. You got sulfate hanging out. And then of course you also have water. So when you go and find your SOA, right, working your way down, copper 2 is right here. That's your SOA. SOA, so it's going to be reduced. And then zinc is here, so that's your SRA. So it's going to be oxidized. So I could actually work my way through this. So this is my anode, which makes it negative. And this is my cathode, which makes it positive. Electrons going from anode to cathode, right? So going from one to the other. What else to tell you for this? The anode is going to be shrinking over time, right? Getting smaller, while the cathode should be growing as time goes on. Again, fat red cat, so it's getting bigger as time goes on. I actually get this like full negative loop going on when it comes to cells. So the electrons are going like this, but I actually have anions completing that negative loop by going towards the anion, or the anode, sorry. So this is my negative kind of circle going on. And I also have cations going towards the cathode. So anions to anode, cations to cathode. Okay. Good for the cells?
Sure.
Yes. Voltaic, decent. Definitely something to try out. Diploma loves the reference cell thing. It's just, they always have one. I feel like it's really silly, but that's fine. They're obsessed with it. What it is that hydrogen was been picked like a zero, right? It's your zero cell. And the reason why is hydrogen is your most basic element, right? It's as an ion, one proton, it's very simple. So it's set as zero. But what if we picked something else as the new zero? What would that change other values to be? So if zinc was the new reference half cell, if I picked zinc instead, how would that change the other stuff? So what would iodine become? So if I take a look, zinc has a value of negative 0.76 volts. So if this is the new zero, what do I do to everything else? Yeah, you subtract the negatives, you're adding 0.76. So all you do is you subtract the voltage value for the new reference half cell from everything else. Okay, so subtract. So now if I look at iodine, iodine was positive 0.54. So now I'm subtracting negative 0.76 volts. So that means it's now positive 1.30 volts. So that would be the new iodine value. Important to note that if I'm looking at a full cell, the voltage for the full cell does not change. Because both half cells will shift, right? Both half cells will now be a new value of subtracting the zinc from both of them. So the actual difference between the two will remain the same. So we'll change half cell values, but not full cell values. So big thing, and if that was confusing, definitely take a look at it later on. The diploma always has one of those. All right. We're in a pickle here. Now we're essentially at time. We're 5 minutes until time, but we have a few slides left. Skip this. Okay, well, so here are two options.
So we pick it up tomorrow.
Yeah.
So what we could do is we could start 15 or 20 minutes earlier tomorrow for those that want to come for the end of this, right? Or we could just finish it up now. Doesn't matter to me, or both. Do two presentations of it, I don't care. How many people are just okay? And I mean, if you're just like, well, I think I'm good for the rest, then that's fine too. You can take off. It's all good. I think I'm looking at 15 more minutes here.
More.
So 10 minutes extra.
Tomorrow.
Are you okay, Arnett?
I have to go do something, that's why. But I don't want to miss this, so if I have to stay, I'll stay. But.
No. It's fine. The other option is you now have the handout, right? So if I'm here a little bit early tomorrow and you have to leave, then you can always also actually look at that. Another thing is right now this is recording, right? So actually, today, I'll be putting this on YouTube. And you can watch the end of this as well.
Okay.
All right?
That's.
Much of like stuff.
Wait, you got a YouTube channel, by the way? You got one?
Yeah, it's got like 2 or 3 followers from these really good vlogs that I was doing for grade 9
Yeah.
until I realized no one was watching them. So I stopped making them.
Alan, you should have done that the whole year. Miss Edmondson did that for us in Bible. Actually,
Really good, eh?
oh yeah.
Yeah.
It was like
the
a
grade 9
really
vlog
good
thing did not help at all. Yeah.
Are you saying?
Giant waste of my time. That's okay.
I don't think he is.
Okay, anyways. What we do to find the cell voltage for the full cell is we do cat minus and. What I like to think of for this is I think about the facts that cats are great, normally positive, and ands are normally negative. So I already know what I'm going to do. I'm going to subtract or take away and, the negative thing, right? So cat minus and. So when you find the voltage, you are just taking the difference between the two of them. Voltaic cells will always come out to a positive voltage, while electrolytic will have a negative voltage. So if you get a negative value for something that's voltaic, you know you messed up. Okay, and you can switch it out afterwards. So I think the next slide hopefully is an example of finding a voltage for this, yeah? So voltage of aluminum, aluminum chloride, nickel 2 chloride, nickel. So right away, what's beautiful about this is I actually know that aluminum is the, well, you tell me, anode based on cell notation. It started out at the beginning. Well, this is my cathode. So I have the cell. I just normally write this as cat minus and. To me, that just makes sense. That's how I think about it in my head. So I'm going to go the cathode reaction. So I'm going to look for nickel 2. Nickel, okay, nickel 2 plus 2 electrons, nickel, that's negative 0.26 volts. Minus my N, which is aluminum, and that's negative 1.66 volts. Notice how I wrote this, that I put the last one in brackets so I know I'm subtracting a negative. In other words, you're adding it. So just be really careful with your negatives for this. But essentially, this will work out to be positive 1.40. Does that sound good for a voltaic cell? Yeah, it's positive. It's good. Okay. Here are the differences between the two. So voltaic is spontaneous, electrolytic is non-spontaneous. Voltaic has a positive, electrolytic is a negative. Now, what is the same is in both of them at the cathode, reduction takes place. The cathode is positive for a voltaic, it's negative for electrolytic. Structurally, this is the major difference, right? The panic thing, so positive anode, negative is cathode. Okay, and then I have electron movement being the same for both, and then ion movement also the same. Make sure you know the differences, really important. That and the energy conversion taking place, and that's critical. All right, we talked about this already. The other thing that's a big clue for you that it's electrolytic is it will be connected to a power supply. What could a power supply look like? Could be a battery, so you might see a symbol that looks like this, right? Do you know which one is the positive? Big one. Positive, right? Bigger. So positive to negative. Another thing you might see is actually just literally a box that says power supply, right? So they could do that as well. Okay, it will most of the time not have a porous boundary because there's no need. OA and RA can be together because it's non-spontaneous. And again, they convert electric to chemical energy. So, just looking at this right away from the cell notation, what indicator do you have that this is electrolytic? What tells you this is electrolytic by looking at it? No porous boundary, no double line. So because I have everything together in one electrolyte, that's a good indicator that it's electrolytic. And that's the same, right? So I wouldn't be getting a voltage out of it if it was voltaic with both anode and cathode being the same. All right, there's some exceptions, right? Do you remember inert electrodes? Carbon, platinum, palladium. Okay, could have that. All right, predict the reactions of the cathode and anode and net reactions. What I would do here is I would actually list my major entities for this. So I'd say, okay, I got some lead, maybe solid. I have CO2 positive. I have Cl minus. And I have water. So these are the major entities I have present. So going from the top down, I find CO2 positive right here. So that most likely is what I'm dealing with for my SOA. So that's that. And then going from the bottom right up, I find lead, and the lead sulfate one, but I don't have sulfate. Find lead just kind of a little bit above the cobalt one. So that is my SRA. So at the cathode, on my cat, I got reduction taking place, so I have CO2 positive aqueous, plus 2 electrons, gives me CO solid. And then for my oxidation, my ox, I have the lead, so I have Pb solid, produces Pb2 positive aqueous, and 2 electrons. So again, reduction at the cathode, oxidation at the anode. My net, really simple, I got 2 and 2, it's good to go, it's good to mix. So CO2 positive aqueous, Pb solid, mix, CO solid, and Pb2 positive aqueous. What minimum voltage is required? Well, I just got to now take a look and do cap minus N. So I have my CO2 positive of negative 0.28 volts, minus my N, which is the lead, which is negative 0.13 volts. This will come out as a negative value, but that's what I want because it's electrolytic. It needs a voltage. So this will come out to negative 0.15 volts. That makes sense though, because this is a requirement. I need 0.15 volts going into this at least to make it happen. Now, an electrolytic cell, it's binary. It's either working or not working. and you got to be this high to ride. Okay, so if the voltage is 0.15 or above, it's going to go. If it's below that, it doesn't go. Higher voltage does not mean it happens faster. What determines how fast it happens? Current. We're not doing the drawn label, no. Refuse. Not happening. No, no. Okay, cell stoic. You will have a cell stoic question. Biggest confusion for cell stoic is actually this. Cell stoic has to be done with a half reaction. Half reaction. You need to have electrons in there as a term. Okay, so cell stoic. Must use a half reaction. You sometimes, before you start, have to build your half reaction just from the information. Normally it's not tough. What's wrong with the time right now? It's in minutes. What does it have to be in? Seconds. The reason for that is amps per current is actually coulombs per second. Okay, so it has seconds built in. So amps is kind of a simplified unit. It's really coulombs per second. This is in milliamps, so I have a little bit of SI prefix stuff going on for the unit. You got to change that to amps. So I think this is a good chance for you to try to. Oh, this is ugly though, because it doesn't say. Just goes to moles. It's not full stoic. We're gonna. Oh, this is better. This is better. All right. So let's actually deal with this first, and then you can try out the next one. We'll take it out, and then we're done. Hey, that wasn't too bad. Easy, easy. Okay, so let's do this one together. How many moles of electrons are supplied to an electrolytic cell? The 200 milliamp hour supply is on for 35 minutes. So how I calculate this is moles of electrons is equal to IT over F. You've got to memorize this one. It's not given to you. You got to full on figure it out. Just memorize it. The way that I remember this, probably not helpful at all, but I say NIT, N-I-T, okay, NIT, and then effort, and then I imagine I'm talking to a grandma, and like being really rude to a grandma, and the fact that that's really perverse and horrible, and I would never say that to a grandma, makes me remember it more than otherwise. Be nice to your grandmas, okay? Don't say those words to your grandma, that's horrible. So, N is equal to IT over F. I have an I of 0.200 amps. I have a time of 35 minutes. So that's 3,500 seconds, right? Oh. 60 seconds in a minute. So 35 times 60 is 2,100. Your F value comes from your data booklet. You actually have it in there. You don't have to memorize it. That's 9.65 times 10 to the 4 coulombs per moles of electrons. So it's essentially how much charge is in a mole of electrons. It's converting between moles and charge. Okay. Kind of a calculator. It's funny, I haven't had to use it this whole chapter until now. Very math-like chapter.
Nice, is that?
0.00435 moles. You're going to get numbers that seem small with this, and that's because it takes a really long time to get a mole of electrons from a current. Okay? Now I can convert between moles of electrons and moles of other stuff with the molar ratio, just like anything else in stoichiometry. So, now that this is done, can we try out the next one? I'll give you a head start. I'll do the solution on the board. You'll check it. Then we're off to the races. We're done. You know, the biggest thing for any test is learning to have confidence around it. You go in thinking this is going to wreck me, yeah, it's probably going to wreck you. But if
just go in with low expectations and then you're proud of yourself when you do better than what you thought. That's what I do.
okay, so you just think you're going to do bad, and then you go in there and it's a nice little surprise.
Yeah, because like if you look at my math, I thought it was really easy, and now I'm terrified that I thought it was that easy.
Right.
So.
Right.
I go in with low expectations, so you exceed them.
Or you can go in just thinking I'm going to kill it, and then you just kill it, and then everything's great.
You don't feel it when you're sad.
Yeah.
So actually, what this is showing is you're more worried about your feelings than you are about your test performance. You're more worried about being disappointed by your performance
Yeah.
than actually the performance itself. That's interesting. Okay, but like if you want to get good grades, what you want to do is you want to go in there thinking like, I'm going to do really well at this. Because being positive in your head allows you to actually remember things a lot better. Positive brain state. That if you're like, oh, I suck at chem, this is going to be horrible. It actually makes your brain worse at remembering the things. So having a bit of positivity, thinking going into it that I have the tools to figure out every question on there. Because like you've been in class, you've heard everything. You've tried out almost every type of question you can have, right? So you just got to go in there thinking that, focusing on that, and hopefully it will work out. Positivity.
I'm relearning this about course.
Well, you really only have 3 days.
Including yesterday.
Oh, okay.
We should have
Get there. It's all good. It's all good. Molar Ratio actually appears often on the diploma. They really like it. The reason why is it was revolutionary and made aluminum super cheap. It used to be incredibly expensive, but then using this method of dissolving it in a molten cryolite or whatever it was, actually made it so that it could, at a very relatively low temperature, dissolve aluminum oxide in a molten state so that aluminum could be produced. So you might be thinking, well, what's the half reaction for this? Well, it's aluminum ion to aluminum. I put liquid because it's molten, right? Not that that would matter at all for anything. Some little details. The 150 amps is actually going to go under the electron section. This is electron information, so 150 amps. 4 minutes, so my time is 240 seconds. I want to know how many grams of aluminum I would get. So I'm looking for mass, and I have molar mass of aluminum from the data booklet. So I'm off to the races. We can calculate moles of electrons. Design T over F. So 150 amps multiplied by 240 seconds divided by 9.65 times 10 to the 4 coulombs per moles electrons. Sorry?
0.737.
Now I can use my molar ratio. So I have 0.373 moles of electrons multiplied by 1 aluminum. For every 3 electrons I put in, 1/3, 0.124 moles of aluminum or mass. Moles comes from the mass, so 0.124 moles multiplied by 26.98 grams per mole. What do I get? 0.36? Sure.
I'm done responding my answer.
Confidence.
Yeah, see, you keep it positive, then you get the right answer.
Jeez, much
I'll be a
worse.
good old Cathode.
All right.
Good one.
Yeah, I don't know, that's it. Any questions?
When you were talking about what was the minimum voltage needed,
Yeah.
and it was negative 0.15, does that mean it can be more negative or it can be more positive?
No, that's, okay, so the negative just means that it's non-spontaneous, so it's a requirement. That doesn't have to do anything with like the hookup or whatever. Okay. But 0.15 volts is how much would have to be at a minimum supplied by the power supply in order for that reaction to happen.
So it can supply a voltage that's more positive than greater.
Yeah, you could do a voltage in the power supply of, let's say, 0.5 volts, and then it would go. But if you only gave 0.1 volts, it would not go. It's not enough energy to pump the electrons the direction they need to go.
Okay, so the negative is saying that you need that,
Yeah, negative is saying it's a requirement.
not that you need negative 0.16. 0.16.
Okay, so negative, yeah, negative is just saying it's a requirement.
Okay.
It's a in. Well, positive means it's being produced. It's an out. You could also think about negative as the fact that you actually attach it differently. So if you've ever attached a voltmeter the wrong way, it'll give you a negative instead of a positive voltage reading. And think about the panic of positive is on anode, negative is on cathode for electrolytic. So you could also think about it as a negative in the ejector. That's another way to think about it. But really it means it's a requirement.
This is
Yeah, so hopefully this is helpful. The crash course thing on Monday, I think is particularly amazing for your diploma. If you were going to choose one other session, please come to that one. Okay, really good presentation. I cover the stuff I think is going to be on the diploma exam specifically, but hopefully you're finding value in all of this. Okay. See most of you tomorrow. What time is it tomorrow? Yeah, Monday's 3 to 5, 10 to 2 tomorrow. And a half-hour break in the middle. Okay. Yeah, hopefully I'll have it posted. We'll see how this YouTube posting goes, how long it takes. Yeah.